Hey kids, Charlie Abuso here again. We're going to finish up the Thermochem notes. We're going to be at number 97. You're going to need to have a calculator. You're going to need to have your reference table. And we're going to do some math. All right. Thermochem, the hardest part is figuring out what kind of formula to use and what kind of mathematics to do and what is the question really asking. This says here, if you combust 8.44 moles of methane, how many kilojoules were released? Now, honestly, looking at this question, how could you possibly know? You can't know. You should say to yourself, I don't know what to do. And when you say, I don't know what to do, that means go to table I. The very first reaction is the combustion of methane. Now, what does it tell you? It tells you that when 1 mole of methane combusts, it releases 890.4 kilojoules. So we're going to do what's called the mole ratio. The mole ratio we use in stoichiometry. The thermochemistry is actively involved in this as well now. It's the thermochemical mole ratio. The moles of methane are in proportion to the energy. And it clearly says 1 mole of methane in this balanced equation, and the energy associated with when 1 mole of methane combusts is 890.4 kilojoules is released. So we have, I'm going to try to write on this real quick. I don't really like to write because it never looks that good, but here we go. We write mole ratio to remind ourselves we're using moles. What are we looking at? Moles of methane as in proportion to energy. 1 mole of methane is going to release 890.4 kilojoules. How do I know that? The number is right here. I don't know it. I put my finger in a box and I write it down. Now this question is about 8.44 moles. Look, 8.44 moles has to be in proportion to a certain number of kilojoules that's equal to the mole ratio we get from the balanced equation. The 1 to 890.4 is in proportion 8.44 to x. Now, how do we deal with this? We have to cross multiply. And by cross multiplying, we're going to get 890.4 times 8.44. And that's going to, and it's kilojoules. The 890.4 is kilojoules. We get this crazy number, which we round to 3 significant figures. So when 1 mole of methane burns, a certain amount of energy comes out. When 8.44 moles of methane burn, this is how much energy comes out. It's not hard. It's a proportion. Proportions are fun. If you combust 40.8 moles of glucose, how many kilojoules are released? Who remembers the formula for glucose? This is something you knew from way back. C6H12O6. So let's find it. C6H12O6 is right here. It's like the 5th or 6th one down. When glucose burns, it releases 2,804 kilojoules. So the mole ratio of glucose to energy is 1 mole of glucose to 2,804. Now, how did I know it's 1? Well, look. There's only 1 mole of glucose. 1 C6H12O6, 6 oxygens, makes 6 carbon dioxide, 6 waters, and the exothermic energy is 2,804 kilojoules. If we burn 40 of these moles, 40.8, it's going to be in proportion. 1 is to 2,804, as 40.8 is to x. Cross multiply. And the answer comes out like this. Table I gives us about 25 different chemical reactions, and some of them are just fixed physical mixtures of salts going into water with energy associated with it. The chemistry has a mole ratio of moles to moles to moles. Also in ratio, though, is the amount of energy. The amount of energy is in proportion to the balanced chemical equation. Liquid octane, which is the third reaction on table I. Liquid octane is C8H18. Now, if you burn up 12.890, 5 significant figures, moles of octane, how many kilojoules are released? Now, we gotta be a little careful on this one. You gotta put your finger in that box because look what happens. The octane to energy ratio, there's 2 moles of octane. Where is it? Right there. See, there's 2 moles of octane. So in this case, it's 2 moles is in proportion to the energy, but we have 12.890 moles cross multiply. Watch the mole ratio. So when we cross multiply, we're going to get 2x equals this. And then once we do the math and we divide by 2, we're going to get the answer. So x then, when we divide both sides by 2, is going to be just 70,000. This is an enormous number. When you burn octane, a lot of energy comes out. And that makes sense, right? Because when you put octane in a car, when you put gasoline in a car, cars travel really far, really fast, carrying a lot of people and a lot of storage and a lot of suitcases. There's a lot of power in a car. The power comes from the energy released by the fuel, and the fuel is called octane. Okay, it's a proportion. The balanced chemical equation says 2 moles of octane combined with 25 moles of oxygen make 16 moles of carbon dioxide and 18 moles of water, and 10,943 kilojoules come out. 2 moles makes 10,943 kilojoules. So what if you have this other number of moles? You can figure out the kilojoules. Here's the equation. What is the mole ratio of this reaction? It's 2 to 25 to 16 to 18. Look, 2 to 25 to 16 to 18. Now, what is the thermochemical mole ratio? It's 2 to 25 to 16 to 18 to 10,943 kilojoules. It's a proportion. The energy is in proportion with the thermochemistry. The chemistry and the heat are all in proportion. 2 moles of octane produce this much energy. You could do anything. What if you only used 1/4 of a mole? Well, it's in a 2 mole to 10,943 ratio. 1/2 a mole would be less. You just cross multiply. It's a proportion. All right. When 7.5 moles of aluminum oxide form, how many kilojoules are released? So when we find aluminum oxide synthesis, which is right here, we see this balanced chemical equation. 4 aluminums, 3 oxygens make 2 aluminum oxides. The delta H is a negative 3351 kilojoules. We can change that. Well, it doesn't have to be changed, but in your head, you can think about it a different way. You can do it this way. 4 moles of aluminum and 3 moles of oxygen still make 2 moles of aluminum oxide, but energy is a product. You could say, delta H is making me crazy. Negative delta H means that energy is a product. So what are the products? Well, one of the products is aluminum oxide. Another product is a lot of heat. The heat, because it's exothermic, is a product. So the mole ratio here would be 4 to 3 to 2 to 3,351. Now, if 7.5 moles of aluminum oxide form, well, let's look at the first equation here. 2 moles of aluminum oxide, what's the amount of energy in proportion to that? 2 moles. Now, there's a boo-boo in this slide. I'm seeing it right now. This is supposed to be a 2. 2. I can't fix this slideshow. I'm sorry. So that's supposed to be a 2. When we cross multiply, we're going to get 3351 times 75 is equal to 2x. Now, there's a mistake here, and I can't fix it. I'm going to have to write on this because I can't let this stand. I'm going to fix this as we speak. So this is 2x, because this is supposed to be 2, because it's in a 2 to 3351 kilojoule ratio. 2 moles of aluminum oxide is in proportion to that. So when we cross multiply, we get 2x. And then, so we're going to have to take this number, 25132.5, and divide that by 2. And the answer, x, is going to be 12,566, but we only get 3 significant figures, so it's going to be 600 kilojoules. We're supposed to have 4 significant figures, 12. Oh my goodness, my poor slideshow. You guys probably think I'm crazy. This is a 5, and this is a 7, and this is an O. 4 significant figures. All right? Sorry about that. Let me leave myself a note. 102 needs to be fixed. 102 fix. Sorry about that, really. What are you going to do? Oops. Still a good person. How many calories removed when 45.8 grams of ice form from water? Now, look at this picture. Take some cold water, throw it in the air. If it's a really, really cold day, as the air spreads out and gets a lot more surface area, the air can freeze it. And you can take a really cool picture like this. If it's a really cold day, use really cold water. You get somebody with a camera, you go out in the yard, you could try this. I'd love to see how you do. All right, couple things. We're going to make ice. We're going to freeze water. We're going to use the Q equals MHF formula. We're going to get the answer to come out in joules, but then we got to convert it. So here we go. Q equals MH of F. How many joules on it? Well, we got the grams, and we got the heat of fusion constant. And with 3 significant figures, the answer comes out to be 15,300 joules. Now, we have to convert this. We have to remember that there are 4.18 joules in a single cal. That's a lowercase c cal. This is not a food calorie. This is a scientific little calorie. So we're going to multiply it by that conversion factor. 1 cal is the same as 4.18 joules. We do some division, and the answer comes out to be 3,660 cals, 3 significant figures. Now, heat of fusion. What is the heat of fusion for candle wax if it takes that many joules to melt the whole birthday candle? Now, there's a little note here. These birthday candles are burning, and there's some melting, but mostly they're burning. We're talking about in this problem, just put the candle on a hot plate and turn it from a solid into a liquid to melt it, not to burn it. But it's hard to find a picture like that. So this is a picture I found because it was pretty. I liked it. But I had to put that little caveat in there. This is burning. We're talking about melting. So if we're going to melt something, we use the heat of fusion formula. The heat of fusion formula looks like this. We're going to solve for the heat of fusion because we know the joules, which is Q. We know the mass. We're going to plug those in, and we're going to do the math now. To get the heat of fusion by itself, we divide both sides by 23.04. And the answer is going to pop out like this. You can solve for anything. You could solve for Q, or you could solve for M, or you could solve for the heat of fusion. The trick is you got to know what formula to use, and you got to do the math slowly and correctly. Here's a can of seltzer. I'm drinking cherry pomegranate right now. That's a mandarin orange. I haven't seen that at Wegmans lately. They're actually having a kind of a run on seltzer. They don't have as much choice as they used to, but this is actually a really good one too. When a can of seltzer is warmed from 293 Kelvin by giving it 64,000 joules, what is the final temperature? Now, this is a hard problem, okay? We're going to assume the seltzer is just pure water. It's really not, but it's close. Got a little flavor. There's probably a little bit of salt in it because all water has a little bit of salt unless it's distilled. But we'll assume it's pure water because this is a math and a thinking problem, not the answer to the secret to life. The question is, what is the final temperature? Well, we're definitely going to heat it up. So we got to use Q equals MC delta T. So we're going to use this formula. Q is the heat in joules. Plug that in. M, we already talked about this. 1 ml of water is equal to 1 gram because the density of water is 1 gram per ml. So the mass is 355 grams. The C value for water, 4.18. joules per gram dot Kelvin. And what the heck is the delta T? We have to figure that out. Think, what is the final temperature? We can't figure what the final temperature is. First, we got to figure out what the change in temperature is, and then we can figure out what the final temperature. So mathematically, we set this up. The joules cancel the joules in the, we divide both sides by 355 and 4.18. The joules cancel, the grams cancel, right? The joules in the numerator with the joules in the denominator. And then in the denominator, we have grams. They cancel the grams in the denominator of the denominator. And so it's going to pop out to be just temperature, and we only have two significant figures here. 64,000 divided by 355 times 4.18 is 1483.9. The change in temperature is 43. Now, one more time, we got to think. We heated the can of water up. The water is 293 Kelvin. We made it hotter. How much hotter? 43 Kelvin hotter. So it goes from 293 up 43 Kelvin. So what is the final temperature? 293 plus 43, 336. Don't worry about the significant figures. Sometimes they're a pain in my neck too. This is what happens in real life. Your starting conditions, you know what they are. You know it's water. You know a constant. You know how much energy you give. You can figure out mathematically what the delta T would be, and then you have to add it to the starting temperature. If it was getting colder, we'd have subtracted. But in this case, since we're making it warmer, the temperature is going to go up. How many grams of water can be heated up by 25.5 Kelvin if it absorbs 17,500 joules? Now, this seems like kind of a what the heck question. What is this? It's Thermochem, right? Because there's joules. We got to think Thermochem, and there's a delta T. We don't even have to figure out the delta T. What is the delta T? 25.5. So we have to use this formula. Q equals MC delta T. Stuff is changing temperature. Q is joules. Plug the joules in. M is the unknown. The question is how many grams? It's water. So the C value for liquid water is in table B, 4.18 joules per gram dot Kelvin, and the delta T is 25.5. You don't even have to figure that out. It's right there. In this case, we got to solve for M. To get the M by itself, we're going to divide by 4.18 and 25.5. Move that onto the other side. The joules in the numerator cancel the joules in the denominator. The Kelvin in the denominator cancels the Kelvin in the denominator of the denominator, and the only unit left is the grams. Now, on the left side, the grams, take a good look at that G. It's in the denominator of the denominator. And mathematically, when you do the calculation, it'll jump back to the numerator then. So the mass is going to end up being 164 grams. What we did here was we said we got this much energy. If we make water change by this temperature, how much water changed? 164 grams. It's about a half a can of salsa. Now, say you got a hunk of copper, 51.1 grams. You put it on a hot plate, you make it hot, and it cools down. It cools down by emitting energy. And if it emits exactly 1,788 joules, if we started out at a temperature, we have a final, what is the final temperature if we have this C value? Now, C value for copper, you wouldn't know it. I'm giving it to you. This is the hardest question so far. Let's go slow. We got a change in temperature problem. Let's go slow and figure out what's the formula. There's only one formula. If we plug things in, the joules, 1,788 joules, the mass of copper, 51.1 grams, the C value for copper. Oh, excuse me, I'm cold. It's making me yawn. The C value for copper is low, much lower than water. It's a given. It's a constant. And then we're going to solve for delta T. Now, the question says, what's the final temperature? Can't figure that out yet. First, we have to figure out the change in temperature. Then we'll get to the final temperature. So when we rearrange this, we're going to multiply 51.1 times 0.39. That's 19.9801. And the units are going to be, the units are a little broken there. Now, in this case, let me draw again. I hate when I make boo-boos. I'm going to have to fix this one as well. I'm going to write myself a little note. I got to fix 107 units. When I rearrange this, when I multiply these two together, these grams cancel these grams. And so this should just be joules dot Kelvin. The grams are gone. And then these joules cancel these joules. This Kelvin is in the denominator of the denominator. And that means it's going to pop out to the numerator. So again, I apologize for these little glitches, but they shouldn't be that big a deal. The delta T is going to be 89.4 Kelvin. What is the question? What is the final temperature? Well, if the starting temperature is 381.5 and it cools down by 89.4, that means the answer is going to be 381.5 minus 89.4, and that's going to be 292 Kelvin. I'm sorry, there's a couple of glitches once in a while. In real life, I can just talk my way through this, but in Zoom-in, it's very hard to go back and fix it. And I don't know how to stop this and fix it. It's just a drag. All right, this is cute because you can see this is an old Disney movie and they're kind of in love and she's about to drop that big snowball down his back. This is a classic trick that people do to each other. You can tell somebody loves you if they put a snowball down your back. If they smash in your face, it's not so good. If they put it down your back, that's the heart. This is a big snowball, 246.4 grams. It's a half a pound. That's a big snowball. This girl's really in love. All right, it's at 273 Kelvin. Luckily, it's a warm, cold day. It's right at the melting point. It's going to drop down this guy's back, and then it's going to warm up to 26.55 degrees. How many joules did it take to do that? Well, first you got to melt it, then you're going to warm it up. So to melt the ice, we're going to use the heat of fusion formula because we use that whenever there's a cold phase change. And then we got to warm the water up. First step, the Q is going to equal the mass of the snow times the constant for the phase changing of water, the cold phase change, 334 joules per gram. The grams cancel, we get the joules. Now, I didn't check the significant figures here. In my head, I'm going to add up all the joules, and then I'll do the rounding at the end. If you decide to round here and round again, you're going to get a slightly different answer than me. That's okay. You can do it all in one big problem, or you can do it in steps and round in between, but the answers will be a little different. It's okay. It's okay. Now, to warm this water up, Q equals MC delta T, because we're going to change the temperature. The mass is the same. The C value for liquid water is in table B, 4.18, and then the delta T is 26.55 Kelvin, 26.55. Then we got to add up the joules. The bell's ringing. My mouth is watering. I'm like a Pavlovian dog. Add them up, 3 significant figures. Now, this took a fair amount of joules. It's a big snowball. They're in love. Love is good. Now, food is energy. I just had myself a roast beef and American cheese sandwich on wheat bread. There was probably about 290 calories in that. What does that mean? Well, calories is a measure of energy. Calories are bigger than cals. Cals are smaller than joules. All these units are all interconnected by conversion factors, but the way we measure how much energy is in food is with the machine called the calorimeter. Now, there's no way to directly measure how much energy is in the food. Scientists have come up with a kind of an ingenious way to figure out how do we measure how much energy is in food. When we eat food, our body digests it. That's a biochemical process. And in that process, the food is broken down into simple substances. Some of it we excrete as waste. Some of it we convert into storage fat. Some of it we just use quickly to regrow and things like that. But some of it's just energy. Food is energy. Food is the fuel. Our car needs gasoline to go. Our bodies need food to go. If you stop eating, it takes a couple of weeks maybe, but you're going to die because you're going to literally run out of energy. And if you don't have enough energy, you stop being alive. If you eat too much food, your body stores more of it and you get bigger. If you eat less food, your body needs more energy and doesn't have it, so it starts to eat itself and you get a little smaller. Food is fuel. We release that energy, not like a car engine that burns gasoline. We release it biochemically. But to measure the amount of food energy that's in food, the calories. We have to use a different process. Here we go. We're going to draw what's called a bomb calorimeter. They call it a bomb calorimeter because literally we blow the food up and burn it up inside the machine to see how much heat comes out. So let me draw you this picture. You draw a picture like this. There's a big tank. The big tank has pure distilled water in it. And they know exactly how much water is in it. They use a really, really good scale so they can measure exactly how much distilled pure water is in there. In the top, there's a very expensive thermometer that's very, very accurate. And you know the starting temperature. Oh my gosh, it's so cold. I'm yawning. I apologize. I'm just a person. I'm not an actor. There's no cut in take two. We're just going to keep going. The thermometer will accurately measure the temperature of the water. So you know exactly what the temperature of the water is. You know the mass of the water, and you know the temperature of the water, and you know it's pure water. Now, there's also a little propeller in there that stirs the water around to keep the water in a good mix, because sometimes it's just colder at the bottom and warmer on the top. So you mix it up so the water is sort of all average. Now, inside of this container of water, there's the bomb, the thing in the bottom right-hand corner. This is a sealed container that goes inside the tank that you put the food in that you want to measure. Maybe in there you would put my roast beef and cheese sandwich on wheat bread. Now, you pump it up, this little container, you pump it up with oxygen. So there's sufficient oxygen to burn through all the food, because there's no oxygen getting in there, it's underwater. And then you run some electricity into it. You get these special rods that go in that are insulated so they can spark the food in a lot of oxygen. So you set this all up, you get your food in the bomb, you put the bomb in the tank, you know exactly how much water is in it, and you know exactly what the starting temperature is, and you keep stirring the water so you really get an accurate reading of the temperature. You get your food that you want to measure in the bomb, you pump it up with oxygen, so when you do decide to spark it with the electricity, it burns to a crisp. Now, your body can't burn stuff. When I eat my roast beef sandwich, there's no fire in my belly. That sounds good, but that's not really what's happening. But whether you burn the food or you biochemically digest it, you get the same amount of energy out. So when you set this whole system up, you're going to spark the food with the electricity. You're going to send the spark in. The food's going to catch fire. There's a lot of oxygen. It's just going to burn, 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 burn. And the fire is going to burn and be hot. And that heat is going to spread into the tank of water. And the temperature of that water is going to go up, and you're going to measure it. You're going to know the starting temperature, and then you're going to figure out how hot does it get. What is the hottest temperature the water gets? And that will be a delta T. You know the mass of the water. You know the C value for the water. You're going to measure the delta T for the water, and you're going to do the math, and it's going to equal Q, the number of joules that the water gained. And then you're going to convert your joules into calories, and you convert your calories into food calories, and you can print your food label, and you're in business. So let's see what happens. Let's assume there's exactly 2,120 mLs of water. 4 significant figures. Take 3. The water starts at exactly 295.0 Kelvin. 4 more significant figures. You're going to burn the food up, and the heat from the burning food makes the water in the calorimeter get hotter. How much hotter? Well, it went from 295 up to 354.5. How many calories with a capital C of energy did this food sample have? So Q equals MC delta T. That's going to be our formula. We can't figure out calories. We got to figure out joules, and then we'll convert it. One thing at a time. So what's the mass of the water? 2,120 grams. Is it water? Yes, it's pure water. So we use the 4.18 joules per gram per Kelvin constant. What is the delta T? That's the 354.5 minus 295. So the temperature of the water goes up 59.50. In order to do that, in order to make that much water, change temperature by this much Kelvin, it would require 527,265.2 joules, which we're going to round at the end, but because we only have 4 significant figures. But now we're going to convert these joules into cals, because we know that 4.18 joules is a cal, and then we'll convert again. So when we do this, it becomes 126,140 cals. Now to figure that out, there's 1,000 cals in 1 calorie. That means it's going to be 126.1 food calories. So if you put my roast beef cheese sandwich in there, I'm thinking it's like 290 calories. That would either make the water even hotter, right? Or I could cut it in half and put a smaller piece of my sandwich in. But if you're going to sell food, you got to know how many calories are in it. It's by law. You got to put it on the label. You're going to have to pay somebody with a good calorimeter to measure it for you, probably 10 times. And then take 4. And then you can print your label so you can tell people who are buying it how many food calories they're eating. But to do that, you use a calorimeter. You measure how many joules of energy the water gained from the burning of the food. Then you have to convert your joules into cals and your cals into food calories. All right. We're going to copy this quick curve, cooling curve for chromium. We're going to put the labels in, and let's get this going. This is a cooling curve for chromium. You have to write the title, and there's a whole bunch of blanks. But the graph looks like this. We start at some really hot temperature. It comes down to B. B to C, that's the condensing point. That's where chromium gas is going to condense into a liquid. At C, it's all liquid, and the temperature is going to drop because we're removing heat at a constant rate until it hits D. D gets flat for a little while. It's a smaller step. And then once it's all solid, it goes from liquid to solid from D to E. And then it gets to be a solid. It gets to be as cold as you want, as long as you don't get to absolute 0. So let's answer. Take 5. Let's answer these questions. What temperatures are on the y-axis? I have no idea. I don't know these numbers, but I do know what they're called. For chromium, they're called the boiling point and the freezing point, or the melting point. So that's what we have. Chromium is element number 24, and I have the melting point, which on our graph is the freezing point, and I have the boiling point, but on our graph it's a condensing point, and I'll pop those numbers in, which I got directly at a table as no thinking, just touch the fingers on the box. Now, what is the potential energy doing from B to C, and what is the potential energy doing from C to D? The temperature is steady, both the flat steps, but we are removing energy. But if the temperature's steady, the kinetic energy's steady, something's got to give. The potential energy is going to decrease. And then from, we got the same letters here. BC and CD, they're both going to decrease. Oh, look at this. I got the answer for C. What is the kinetic energy? I don't even know what's going on. You know what? I think there's another mistake. This PE from C to D, which is correct, we're supposed to show, no, I guess that is right. The potential energy is steady there. I'm getting mixed up. There's too many letters. What is the kinetic energy doing from A to B? Well, temperature's dropping. That means kinetic energy is dropping. And from D to E, the kinetic energy is steady because the temperature is steady. And so let's see what we got. Up on top, the kinetic energy drops, and then D to E, kinetic energy is steady. Now, this is better than I thought. All good. Why is BC, the top flat, longer than DE? Now, on a cooling curve or on a heating curve, it's the top phase change that's always longer than the bottom phase change. And of course, you know the answer by now. BC represents condensation, and the change for chromium, in this case from gas to liquid. The hot phase change is a much bigger energy event. Okay, much bigger. So it's longer because we have to remove more energy to make that happen than we have to do to make the chromium actually freeze. Propane gas. on table I. Uh-oh, we got to switch back. This is a jumpy class. We got to jump around over and over. Propane, C3H8. It's the second one. Second line. And it says here, when 1 mole of propane combusts, 2,219.2 kilojoules are released, right? But this question's about 5.75. So we need to do a mole ratio. Well, first we're going to do this, I guess. That's what it looks like with the negative delta H, which we could rewrite with energy as a product. And we should be able to see here that when 1 mole of propane combusts, 2,219.2 kilojoules is a product. So we're going to look at the mole ratio between the moles of propane and how much energy comes out. So this is going to be 1 to 2,219.2. This has to stay in proportion in the problem. In this problem, we're going to burn up 5.75 miles of propane. How much energy is released? 1 is to this, as 5.75 is to that. We cross multiply, and then we round to 3 significant figures. So if, in fact, you combusted nearly 6 moles of this stuff, you're going to get a lot of kilojoules coming out, right? Almost 6 times as many, 5.75 times as much energy comes out when you combust this much, as opposed to when you combusted just 1 mole. How much energy is absorbed of the reaction of 99.0 moles of HI gas forming? You say, I don't know. I don't know either. The heck. This is the last chemical reaction before we get to the physical changes ones. So we have it. It says in this balanced chemical equation, H2 and I2 makes 2HI, and the delta H is positive. So in this case, we can rewrite it, but energy is a reactant. When that means it's going to absorb energy. Hydrogen and oxygen have to get energy in order to make HI. So the mole ratio here would be 53 kilojoules to 1 to 1 to 2. But this question's not about 2 moles of HI, because see, we have 2 moles of HI. The mole ratio here is about 99. So let's look at the second blue line to see what's going on. The HI gas to energy, 2 moles of HI gas form when it absorbs 53 kilojoules. But what if 99.0 moles of HI form? How many kilojoules? Cross multiply, solve for X, 2X equals this, divide by 2, and with 3 significant figures, X equals this, 2,620 kilojoules. Table I gives us a balanced chemical equation with energy associated in proportion. And then we're just doing a proportion here and figuring the answer out in exercise in mathematics. 45 grams of an unknown metal absorbs a lot of kilojoules. Now look at that, 1.51 kilojoules. I don't like that number. We're going to turn it into joules in a little while. The temperature changes. What's the specific heat capacity constant? And it says, note, kilojoules. That's not joules, kilojoules. Now, temperature changes. Got to have Q equals MC delta T formula. Now, I don't like 1.51 kilojoules. Q, as you remember, and we wrote it down, is the energy in joules. This says kilojoules. So first step, get rid of these freaking kilojoules. A kilojoule is 1,000 joules. So we're going to change that to be 1,510 kilojoules. We're going to convert it right into joules. The mass is given, the C is the unknown, and the delta T, that's 345. I'm going to show you 345. Take away 268. 77 is the delta T. We got to get the C by itself. So we divide both sides by the mass and the temperature. And the answer is going to come out. Look at these beautiful units. Joules divided by grams times Kelvin. And that's going to come out to be 0.435 joules per gram dot Kelvin. In this case, we knew everything that happened. We used that to figure out what is the constant for this particular substance. The variable happens to be the constant. If we knew what it was, we could look it up on a table. We could just look up. We don't know what it is. So we did this experiment, got all the data, and we worked out what is the constant. Now, these two things you got to memorize. The first one you should already have in your head. The second thing we've already talked about, it should be in your head, but let's get this going right now. The law of conservation of matter says matter cannot be created, destroyed in a chemical reaction or a physical change. And a physical change is a phase change. If you got stuff, you can't lose it. It's going to stick around. It can change forms. It can bond in different ways and make new stuff, but it's the same amount of stuff. If you're making a phase change, you're going from solid to aqueous or solid to liquid by heating it, or liquid to gas, or vice versa. You can't lose your matter. Now, the law of conservation of energy is similar, but it's different, right? Energy cannot be created, destroyed in a chemical reaction or a physical change, but it can be transferred. You can make heat energy become motion, right? Or you can make sound, energy that's coming out. It can be sound energy, light energy, heat energy. You can convert it back and forth. Different kinds of bonding energies can be released as heat, or energy can be absorbed, making things cold, but actually the energy is then trapped in bonds. So you can transfer energy, but you got to keep track of it. And we're going to keep track of it. Can't lose it. Which takes more energy, melting 50 grams of ice or vaporizing 50 grams of steam? Now, there's two ways to do this. You could do two big math problems, or you could say to yourself, wait a second, how much energy does it take to melt ice? Well, to melt 1 gram of ice takes the heat of fusion. To vaporize 1 gram of water takes the heat of vaporization. Whether it's 1 or 2 or 50, melting is less energetic and vaporizing takes a lot more energy. So look what I got here. Vaporizing a single gram takes 2,260 joules, and melting is 334. So the hot phase change always takes more energy. If you have 1 gram, 50 grams, 412 grams, doesn't matter. The 50 grams didn't matter. Which takes more energy? Heating up 23 mLs of water by a little bit, or heating up 23 mLs of water by a different amount? Well, what are the delta T's? In the first one, the delta T looks to be, I could do this in my head, but I don't want it. 299 minus 274. The first one has a delta T, and I'll write this down so you can see it. The delta T equals 25 Kelvin. And this one, 323 minus 299, 323, oh, come on, calculator, 323 minus 299, the delta T is going to equal 24 Kelvin. So the question says, let's see what this question says, which takes more energy? Well, liquid water stays liquid water, warming it up. The one that makes it change temperature more is going to obviously take more energy. So that's going to be, let me see if I can get these drawings gone, annotate, clear all drawings. There we go. That's 25, that's 24 change. So the smaller delta T would require less energy. The larger delta T would require more energy. Which takes more energy, vaporizing this much water or changing the temperature of a lot of water by 97 K? Well, this time we got to do the math. Can't do this one in our heads. There's no proportion. To vaporize 21 grams, it's going to take 47,460 joules. We use the heat of vaporization formula. To warm up 100 grams of water by 97 Kelvin, we're going to use the delta T formula, and that's going to be much less energy. Heating up water just means shaking it more. Vaporizing means blowing it apart. That's always a really big energy event. It's hard to vaporize water. That's why you get burned so bad when it condenses, because all the energy you took to vaporize, that's how much energy comes back into your hand if it ever condenses on your hand. So in this case, you got to do the math and the answer just pops out. Now, this is an old Regents question. Which of these 4 samples has the lowest average kinetic energy? Now, we get different volumes, different temperatures. This is very confusing, right? No, it's not. Average kinetic energy. Temperature's down, kinetic energy's down. So we're looking for the lowest temperature without any problem. The lowest temperature will have the lowest average kinetic energy. That's how it works. It's average. It doesn't matter what the volumes are anymore because we're using the average. That means we have equal comparisons. We're only going to look at the temperature. Kinetic energy and temperature are always in hand. They do the same thing. I think this is the last slide or two. This horse has a boo-boo, kicked himself in the leg. So they got an ice pack on his leg. What is going on? Describe the thermochemistry. Is the heat flowing from the ice to the leg, or is the cold flowing from the ice to the leg? Or does the heat flow from the leg to the ice pack, or does the cold flow from the leg to the ice pack? What's going on? All right, C. Okay, cold doesn't move. Cold is a lack of energy. Heat can move, and the leg is hotter than the ice. So there's no heat in the ice compared to the leg. All right, so the heat will leave your body. It'll make you colder, but you don't get colder, you get less warm, and you feel colder. The cold does not flow. The heat is energy, and the heat can be transferred. Now, there's an old chemistry adage. I like that word, adage, and you need to remember this because this is important. When bonds form, energy is released. When a bond forms, extra energy is released because bonding is stable. When things are kind of cool and bouncing around, they got some energy. When they bond together, they're more stable. They release that energy. And a good example of that on the synthesis of water. Remember on the first day of school? And again afterwards, I blew up a balloon of hydrogen, and it was so loud we had to protect our ears. When the what? Carbon dioxide forms? Who typed this? Water forms. I don't know what that is. This is another boo-boo there. When the hydrogen and the oxygen bond together tightly into water, water is so stable, it releases that extra energy as light and sound and heat. All right. Lastly, the change in temperature in centigrade is the same as the change in temperature in Kelvin. The delta T's are the same, not the temperatures. Look at me and you. You're probably 16 and I'm 60. And in 4 years, if we add 4 years to both of us, you'll be 20 and I'll be 64. We'll still not be the same age. We'll still be the same difference apart. How much difference apart? Well, we both gained 4 years here though. So the change in age is the same. Centigrade and Kelvin are 2 different scales. Centigrade's up here, Kelvin's at the bottom. They change together, but they're not the same temperature. The delta T's are the same, but the temperatures are different. And that, my friends, is the end of thermochemistry. Do your homework, read the basics. Never quit. It's a hard year. We're doing our best. You are, I am. Some days we're better than others for you and me also. Some days are hard for me. I make dopey boo-boos. I'm gonna have to go back and fix these slides, but it's too late. They're already in the Zoom. I think you're wonderful. Hang in there.